Hello, in this video we're looking at definite integrals. This is our first introduction to this topic. We're leading up to it in some previous work. This is our first look at it. So like I said in previous work, we had looked at sums of the following form. So not getting overwhelmed by the notation here. Remember, this means that I start from 1, counting up, would be f of x1 star times delta x plus f of x2 star delta x plus all the way up to n total terms. So this is just that notation, that sigma notation. We looked at those. Formally, this is called a Riemann sum for this function lowercase f. And we said we previously looked at, and one thing you can think about, try to remember, for positive f, or at least we can get by with non-negative f, this is just the formula for the area approximation by rectangles. Here's your rectangle height, here's your rectangle width, and we're adding all those up. So here's our formal definition for the definite integral. So if f is a function defined on the closed interval a to b, okay, we've got delta x as we defined it before, so nothing new there. So all our key points here. So positive integer n. In our first interpretation, that would be the number of rectangles. If xi star is any point in the ith subinterval, remember that's called the sample point. Then the definite integral of f from a to b is given by the following. So the left-hand side of the equal sign here, left-hand side of the equation, if you like, this is just the notation. We've got this tall, skinny little s-looking thing. Lower limit of integration is a. That's our left endpoint. Upper limit of integration is b. That's our right endpoint. There's our function f. We say down here f is called the integrand. It equals the limit of that sum. The limit of the Riemann sum is as n goes to infinity. If you like, the number of rectangles infinitely many, you kind of increase and increase and increase, kind of fill in that space to get the exact area if we think back to that earlier application. So it equals that provided the limit exists and gives the same value for all possible choices of your sample point. So like I said, that function, we call that the integrand, and if the limit exists, we say that f is integrable on that interval. So when we were thinking about the area problem, we required f to be non-negative. A Riemann sum using f makes sense mathematically if we drop this condition. So all we're doing is just adding these things up. F could be positive, negative, whatever. We could still add those things together. But if we're thinking about this interpretation, we would need to think of negative area. So really, if you like, we're kind of thinking of a net area. And forgot that I wrote that right here. So looking at a net area there. So net in the sense of, like overall. Let me do a little sketch of what's kind of going on here real quick. So if I had maybe a function like this, I'm going from a to b. So I'm looking at my definite integral is going to involve kind of 3 different parts there. This part will be positive, this part will be negative, and this part would be positive as well. So the definite integral from there to there would give me a negative output, so plus minus plus if you like. But that's what we mean by that net area idea, the overall total. So we're going to learn a number of techniques for evaluating integrals, because evaluating them using limits is very, very difficult. But early on this net area viewpoint, we'll find it to be helpful. So a couple properties getting started. First couple come from this process being linear. So that means is if f and g are integrable, and this we'll have these conditions throughout the properties on the next slides. Then if I have a sum or difference of integrable functions, I can look at them in pieces. This was the same with differentiations, the same with limit computations. If the individual ones exist, we can break that up into those individuals. So the definite integral of the sum is the sum of the definite integrals. Likewise, or not likewise, but similarly to the differentiation, if we've got a constant times a function, and we know that this is integrable, we can always pull that function, pull that constant out. We use these properties over and over and over again. We almost never formally think about them. You think back to when you had something like f of x equals x squared plus 2x. Without thinking about it, if I asked you for the derivative, you'd just say it's 2x plus 2. Well, really what we know is we know the derivative for this guy, and we know the derivative for this guy. But I know that I can add those together. And for this one, I've got 2 times 1 I know, and the derivative of x is 1, so 2 times 1 is just 2. So the idea is we use these properties a lot. Like I said, we don't often think about them. A couple more that are kind of special for definite integrals. This first one, if you think about, if you've got a constant function, the definite integral from a to b, without even doing any fancy calculus stuff, that height is going to be c, that width is b minus a, so that, think of it as an area. If c was negative, it would be this similar type of thing, c times b minus a. For this property, if I go from b to a, so I've reversed these limits of integration. Think about going from b to a, my delta x would have, one way of thinking about it is my delta x would have to be negative because I'm going in this direction. So my delta x would be negative. And so the effect is in switching those limits of integration, if it has the effect of multiplying the definite integral here by -1. For this guy, you can imagine you've got whatever function you like, and you go from a to a. What's the area under that curve? Well, there's no area, there's no width, so from a to a, it's always going to be 0. And for this last one, basically what we're saying is, now c doesn't have to be in between c doesn't have to be in between a and b, but if you break it up, the integral over this part of it, the whole thing a to b, is the same as the integral from a to c plus the integral from c to b. That's what we're looking at there. So those properties should also kind of make sense. Finally, we've got a couple of comparison properties. These ones we won't walk through as closely. But if f is non-negative, then the definite integral is going to be non-negative. If f is bigger than g for x in that interval, then the definite integral is going to be bigger than f is going to be bigger than the definite integral of g. So you get that preservation there. And then really, this is just an application of the previous one. So you can think of capital M as a constant function, look back at the previous one. Look at lowercase m as a constant function, look back at the previous one. And then for these parts in the inequality there, think back to this property. But if it's bounded by m and m, then the definite integral is bounded by m times the width of the interval, m times the width of the interval. I'm not going to use these nearly as often as these other ones, but we just wanted to get those out there for you. So now, when it comes time to evaluating definite integrals, this is a very difficult process. It involves, at least what we know now, if we're going to do it by the definition, it involves computing a limit. Let me zip way back here. Way back. Okay. Involves computing this limit. So it's kind of like what you do when you do the derivative by definition, limit of the difference quotient. You mess around and you try to get this figured out in a more simplified way, and then you look at the limit. That's what we did with derivatives as well. We cleaned up the difference quotient, then we looked at the limit. Same idea now, but it's even more complicated. So if we have kind of linear, quadratic, or cubic terms, we can use these three, one of these, or depending on what we're looking at, maybe all of them come into play, formulas. So what this is saying is if I add up the first n integers, positive integers, 1 plus 2 plus 3 up to n, here's a nice formula for it. If I add up the squares, 1 squared plus 2 squared, and so on, here's a nice formula, and so on. This is very limiting. We don't have a lot of these formulas, so trying to do definite integral by definition, it's very limited with what we can do. It's really not fun to try to go through that manipulation. We will in a couple examples, but it's not a fun time. And so just to conclude, as quickly as possible, very, very much so, we want to learn how to compute definite integrals without using limit definition. Limits make things work, it makes calculus work, but those computations are very, very tedious at best. So we'll have upcoming videos and talks, and we'll see about how we can do this maybe a little bit faster, but now we just wanted to establish the definition. So this is what we're looking at with the definite integral.